Hello everyone, our project is on early leukemia detection using hybrid vision transformer and CNN models. I'm Darshan Vanushali and I'm presenting along with my teammates Corinne and Sean. We'll walk you through our motivation, the three SOTA methods we implemented, our results across the three datasets, and what we learned along the way. So now let me quickly introduce myself. My name is Darshan Bhanushali and I'm a master's student at WPI studying computer science. I did my undergrad in IT and then spent about 3 years working professionally as a software engineer. In this project, I was responsible for implementing the cytodiffusion model. I'll be presenting our three SOTA methods, the cytodiffusion architecture, how we implemented it, and our results.
Everyone, I'm Corinne Corville, and I'm a master's student here at WPI, studying for the master's in AI with a specification in cybersecurity. I did my undergraduate here as well. I graduated in 2020 with a degree in computer science, and since then I've spent 5+ years working professionally as a software engineer. In this project, I was responsible for implementing the BCCT model and building the shared evaluation pipeline that all three of the models run through. I'll be presenting our evaluation approach, the BCCT architecture, how we implemented it, and our results.
Hello, my name is Sean St. Pierre. I am currently enrolled in the Masters of Computer Science program. I have a background at WPI where I graduated in 2018 with a bachelor's in electrical and computer engineering. Since then, I've been working as a software engineer in industry. Decided to come back and get my master's and focus in AI/ML. Thank you. Our goal for this project was to address leukemia and the early detection of it. Leukemia is definitely an on-the-rise health pandemic with 300,000 new cases each year, so early detection can help get patients preventative care as well as the accommodations that they need. For this study, we identified 3 data sets which focused on ALL as well as blood cell mutations. So the Rabin dataset identified 5 cancerous mutations. The CNMC dataset was a binary classification where it was a cancerous or non-cancerous classification, and then the BCCD was then again the white blood cell, red blood cell versus platelet cells. So the red blood cell, white blood cells would have those blood cell identifications, kind of testing the model's efficacy for classification. This was our way of kind of taking the overarching problem of leukemia and then narrowing it down to a focused research topic such that we could execute it and train the models that you're about to see against this data set. Thank you.
So now let's understand the three SOTA methods that we have implemented. All these three solve the same problem. They take a cell image, they extract meaningful features, predict the cell type, but they fundamentally take different bets on where those features come from. BCCT uses a completely frozen ViT-based 16 model. The backbone never sees a gradient update. Token fusion merges similar token across attention blocks, and a closed form ridge aggression solves the classifier in a single pass. Talking about the second method, which is the cytodiffusion, it basically takes a generative modeling angle. Instead of a vision classifier backbone, we use the encoder half of a stable diffusion VAE, a model trained to compress and reconstruct images. The hypothesis is that a powerful generative bottleneck learns perceptual features that transfer to microscopy, even though it was trained on natural photos. Let's talk about the last method, which is the ViT-CNN hybrid model, which is Sean's method. It takes an ensemble approach. A fine-tuned ViT captures global structure, a CNN captures local texture. Both representations are fused for the final prediction.
We evaluated across 3 datasets, and we chose each one deliberately. The Rabin WBC is a healthy white blood cell classification benchmark. It has 5 visually distinct cell types. It validates that the model can capture meaningful cell morphology. The CNMC 2019 is the clinical task, binary detection of leukemia's blast cells versus healthy lymphocytes. This is the only data set with actual leukemia cells, so it's the only one that matters for our clinical claim. BCCD is a 3-class blood cell data set from a different imaging source. It exists as a generalization check, confirming results don't only hold for one distribution. One of the most important engineering decisions in this project was the shared infrastructure. Each model uses the same data loader, the same preprocessing, the same train-val test splits, and the same metrics model. If we hadn't done that, any difference in performance could have been attributed to the setup rather than the model itself. For metrics, we report accuracy, macro F1, ROC, sensitivity, and specificity. Sensitivity is the most clinically important, as a false negative means a leukemia case gets missed, which is the worst possible outcome. That's why it's the number we'll be paying closest attention to. We also ran low data regime specification on CNMC, 10, 20, and 50 examples per class, repeated 3 times each and averaged. This simulates a hospital that wants to deploy the system but only has a small number of locally labeled examples. One scope note worth stating explicitly is the cell-level classification. Patient-level diagnostic aggregation, deciding whether a patient has leukemia based on cells, is outside the scope of this project. BCCT is a 3-staged architecture, and I'll walk you through it from left to right. The backbone is a frozen ViT base over 16, pre-trained on ImageNet 21K. The weights are completely locked, no fine-tuning, no gradient updates at any point. The model relies entirely on the features that were learned during ImageNet pre-training. Next is token fusion, applied across all 12 attention blocks. A standard ViT processes 197 tokens, 1 CLS token plus 196 image patches. Token fusion progressively merges similar tokens at each block using a merge budget of R equals 16. By the time the images pass through all 12 blocks, those 197 tokens have compressed down to approximately 5. This reduces computation without touching the backbone weights. The final stage is the fixed random classifier, or FRC. The CLS token from the last attention block is fed into the FRC head. Instead, there's a hidden layer with a weight matrix W and bias B, both initialized from a normal distribution and immediately frozen. They are never updated. The hidden output goes through ReLU, and then the original CLS token is concentrated directly via a skip connection, giving a 3,840 dimensional combined feature vector. The output weights F are then solved analytically using ridge regression. This is inspired by extreme learning machine theory. The result shows that frozen random projections are sufficient when the output layer is solved in closed form. The key point, zero gradient-based training. The entire fit is one forward pass on one matrix solve. This was re-implemented from scratch with no official reference code, where no official reference code was available from the paper authors.
So now let's understand the cytodiffusion architecture flow diagram. Cytodiffusion is inspired by work from the Cambridge CIA group. The model they studied is the VAE inside stable diffusion. The VAE's job is basically to compress a full image into a compact latent code and then reconstruct it at high fidelity. To do that well, it must learn to preserve perceptual structure such as shape, texture, and color gradients and edges of the image. The cytodiffusion hypothesis is that this bottleneck, trained on hundreds of millions of natural images, learns representations rich enough to distinguish cell types even though it has never seen a blood cell. The architecture basically has two parts. The encoder, which is fully frozen, takes a 224 by 224 cell image and produces a 4-channel latent at 1/8 spatial resolution 4 by 28 by 28. We apply adaptive average pooling to 8 by 8, then flatten, giving a 256 dimensional feature vector. This is the only input the classifier ever sees. The second part is a 3-layer MLP, which is 256 to 512 to 256 to the number of classes with GELU activations and dropout. This is all that gets trained.
This slide is serving as a brief overview of the Visual Transformer Convolutional Neural Network hybrid architecture. So at a high level, right, starting with on the left, working our way down to the right, essentially we have our input blocks or consumption. You'll notice the resolution of the image is 224 by 224 with 3 channels. This is a deviation from the standard InceptionNet v3 backbone's normal 299 input. However, the white paper that this model was built on specifically called out the dimensions, as it pairs well with all of the data sets that we were using in these experiments. Going now to the backbone that was previously mentioned, it's a hybrid of a pre-trained v3 backbone with roughly 70% frozen layers. So the paper called out freezing up to layer index 200. But for this experiment, we froze up to the mixed 5D layer, which is around 200 or so the documents say. This also provided us with the ImageNet heritage training that InceptionNet has, while still maintaining the residual layers for feature extraction that pertained to the blood smear images. We then do a reshape, which is going to feed into our visual transformer encoders. That's going to then output that 25 by 248 input. It's going to go through a 2 transformer block input with a total of 8 attention heads. The attention heads are then passed over to the classifier, and the classifier for this experiment had both 5, 3, and 2 class implementations each, depending on which data set we were using and the status of the data.
Let me walk you through how this code actually works. Token diffusion is applied by monkey patching Hugging Face's ViT attention module at runtime. There are no changes to model architecture, no custom layers. We replace the forward method of each attention block directly. This means the standard Hugging Face ViT base 16 is used exactly as is, with token infusion injected on top. For training, the process is 2 steps. First, we run the entire training set through the frozen ViT, 1 full forward pass, and collect the CLS tokens for each image. Those become our feature vectors. Second, we compute the hidden representation H, applying ReLU to random projection of each feature, concatenate that with the original CLS token to get our 3840 dimensional vector, and then call the torch library, and then that single line, the LSTSQ call, is the entirety of the training step. No epochs, no learning rate, no backpropagation. For inference, it's a forward pass through the ViT, the same FRC computation in an argmax over the logits. One implementation detail worth noting is that token sizes must be reset between batches. Token fusion trace how many original tokens each merged token represents. And if you don't reset between batches, the size weights carry over and contaminate the next batch. Another detail, this implementation produces a 3840 dimensional feature vector. The paper describes a 3072. The difference is the skip connection. We explicitly concatenate the original 768 dimensional CLS token to the 3072 dimensional hidden output. The checkpoint only saves the FRC weights and configuration. The backbone is never saved because it never changes and gets reloaded from Hugging Face on each run.
Now let me walk you through the implementation of Cyto diffusion and how it works in code. So the first step is loading the SDVAE encoder from Hugging Face, specifically the VAE component of stable diffusion v1.5. Its parameters are immediately frozen and the encoder stays in eval mode for the entire training run. The pre-processing step is subtle but critical. Our data loader normalizes images to dataset mean and standard deviation, but the SDVAE was trained expecting inputs in the range -1 to +1. So before encoding, we undo the dataset normalization to recover approximate pixel values, then rescale it to between the range -1 to 1. If we skip this, the encoder's features are effectively useless because you're feeding it to something that it was never trained to handle. Talking about the feature extraction, it is a straightforward forward pass. It encodes, takes the mean of the latent distribution rather than a sample for determinism, pool, and flatten. The result is a 256 dimensional vector per image. This step runs with no grad, that means no memory overhead for gradients on the large encoder. Training happens entirely on the MLP. Class weights are computed once from training set label counts for CNMC. This roughly doubles the loss contribution from healthy cells, counteracting the 2:1 imbalance. We also clip gradients at max norm 1.0, which stabilizes training when the head encounters large early losses. The key implementation difference from BCCT is fundamental. This model requires backpropagation over multiple epochs. Running every batch through the VAE encoder, even frozen, is expensive. We reduced the epochs from 30 to 10 and doubled the batch size to 64, which brings the training time down to roughly 15 minutes on a T4 GPU versus BCCT, which takes about 3 to 5 minutes. The encoder processes roughly 7,000 images per epoch, and the VAE is a deep convolutional network, not optimized classification speed inference. On saving the checkpoint stores only the MLP weights and the config dictionary. The VAE is never saved because it never changes. Same weights every run, so it is reloaded from Hugging Face.
This slide is going over kind of the high-level implementation for the Visual Transformer Convolutional Neural Network Ensemble model. There's a lot of steps, being that these are two models coming together, reforming into an overarching model, and then a classifier. So there's some pseudocode, some actual code where I thought it felt pertinent to display. So I won't go through this line by line, but at a high level, we're going to start with loading in that InceptionNet backbone. We're going to it's pre-trained, where we have to set the oxalogit flags to true for training. At the end of the training cycle, we flip that back off to false for the inferencing period. We loop through the trained model and basically freeze the layers that we need, and any layers that were not hit are unfrozen, and those are now the layers that will then learn and adapt to the training data. An Atom W optimizer was selected, as this provided the best optimization algorithm. It was a little bit better than Atom, and it was a little bit more performant than SGD. SGD was a little bit more compute intensive, and this aligned with the white paper that quoted this. There is a differential learning rate. The reason being is the neural network backbone is already pre-trained, so it doesn't need as fast or as high as a learning rate. So we decided to scale that one back just to maintain computational complexities. But however, since the visual transformer and the classifier are brand new, they did need a little bit higher learning rates. And a weighted decay of 1 to the -4 was selected. This aligned again with the white paper and seemed to have the best performance. I did play around with this number a little bit, and there wasn't -4 was the most performant on the wide range of data sets. So we're going to go through for each epoch, each image. First, the features are extracted out of the backbone. The backbone is going to output this into that, it's going to reshape it, put it out into that 25248. That is going to then be projected into the the projection step is going to happen, where that's actually going to take the embedded dimensions of the transformer, and that's going to then divide that up by the set coming in. So that's how we get that 25 by 256. These are then passed over to the CLS token is then generated and then prepended to the set. We then get the query key value for the attention scores and matrix multiplies. We then compute that we reorder it to align with the attention heads. It's just the order of the arguments in the array need to align with the attention heads. We then compute the attention scores. We take the common computed weighted scores. We then recombine them out of each of the attention heads, and then we output that into the transformer block. The transformer block is then going to normalize both on the attention, so the multi-attention scores, and the feed-forward network. Then this is going to go through a layer normalization. This layer normalization is, again, the embedded dimension. The CLS token is now extracted, and that is passed over to the classifier. The classifier is then going to perform a linear transformation from 256 to 128. The GLU activation with a 20% dropout is then enforced, and then a final transformation from 128 to the number of classes is the final step of this.
Now let's talk about the results. Our strongest result is Rabin at 95.83% accuracy and 99.43 AUROC. That AUROC means the model almost perfectly separates all 5 white blood cell cases from each other, despite the backbone never having seen a single medical image during pre-training. That result is competitive with fine-tuned models on this benchmark, and we achieved it with zero gradient training. CNMC is the most clinically important result and is also the hardest. This is the actual leukemia detection task, distinguishing blast cells from healthy lymphocytes. We achieved 76.43% accuracy and an 80.38% AUROC. The macro sensitivity is 67.91%, and I want to address this directly. CNMC is class imbalanced. Approximately 68% of the dataset is all blast cells, and 32% are healthy. This imbalance drives the microsensitivity down. The number that matters clinically is all sensitivity, which is 91.3%. We are correctly identifying 91% of all leukemia cases. The drop from Rabin to CNMC reflects the domain gap between ImageNet pre-training and stained blood smear imagery. This is a genuinely harder task. BCCD confirms the model generalizes. 95.68% accuracy and 96.69% AUROC on a completely different image source. The frozen feature holds up across different blood cell datasets, not just the one the model was built for. For the low data regime on CNMC, the trend is what matters, not the absolute numbers. AUROC climbs from 61.1% at 10 shots to 68.6% at 50 shots. That's consistent improvement, and it shows that even with very few labeled examples, the model learns something meaningful. The gap between 50-shot and full training is real. The clinical domain is different enough that more data helps. But the direction is right. The takeaway across all 3 datasets is that the frozen ViT features transfer surprisingly well to blood cell morphology. A model trained on ImageNet with no updates to any of its 86 million parameters still achieves a near-perfect AUROC on a medical image benchmark.
Now let me walk you through the results of cytodiffusion. So BCCD is the strongest result with 99.26 accuracy and 98.05 OROC score on a 3-class blood cell classification task. This is actually expected because BCCD is a small, clean dataset with visually very distinct classes such as platelets, red blood cells, and white blood cells look nothing alike. So even a frozen SDVA encoder extracts enough visual structure to separate them almost perfectly. Talking about the Rabin WBC, it tells a more interesting story. With about 75.36% accuracy and 97.21 OROC score. The high OROC score means if the model ranks classes correctly with near perfect confidence, it knows which class is most likely, but the lower accuracy means it struggles to commit to the right answer when classes look similar. This is the domain gap showing up. The SDVA was trained on natural images, not microscopy, so fine-grained morphological differences between say lymphocytes and monocytes are harder to distinguish from frozen features alone. Talking about the last data set, CNMC, it is a very clinical task. So the leukemic blast cells versus healthy cells, uh, it basically gave an accuracy of 74.86% and OROC score of 72.04%. The model learns the distinction but it hits a ceiling with frozen features on this fine-grained binary task.
So this slide is the results from the Rabin dataset through the visual transformer. Starting from the bottom left, we have the training accuracy or the training metrics. So accuracy was pretty high at 98%. The recall, so the F1 score was again pretty high at the 97%. The ROC score, or the discrimination, was, we're coming in at almost a near perfect classifier. Our sensitivity to identification, our sensitivity to identifying not the target or not the intended class, was also very high at 97 and 99 respectively. These metrics are then kind of reflected in the validation confusion matrix, which we show very high classification performance in this model. The Rabin data set is a larger data set. There is the data is more diverse. There's 5 classes. So this is all kind of statistics that or characteristics that help the model perform better, and as seen by the metrics. Now on the bottom right, there was a kind of how do we apply this to the real world? Because in the real world scenarios, you don't have these massive data sets. So maybe, you'll have 10 data points or 20 or 50, given over a patient's, testing cycles, right? So the 10 shot was a limited data set. Accuracy was still very high. The F1 score is still very high. So we performed really exceptionally with the limited data sets, kind of proving on a diverse data set like Rabin that the ViT-CNN would be successful in detecting leukemia cells or these mutations in PBS imaging. So going into our next data set, which was the BCC data set, which only had 3 classes, platelets, red blood cells, white blood cells. There was a struggle this time. Accuracy was still 97%. However, the F1 score was significantly lower than the Rabin, or I shouldn't say significantly, but about 5% lower than the Rabin. ROC was still high at peak, so over average. And sensitivities also took a little bit of a dip compared to the Rabin. The big thing here is the F1 score on the 10 shot is significantly, it's almost 10% lower than that of the Rabin data set. And I believe this is due to the learning rates and training rates of small data sets, as well as the weighting of how platelets are classified in this. Now, looks like the model is struggling, particularly with the platelet class. This could be just the features extracted. We didn't have enough learning rates on the feature extraction, whereas RBCs and WBCs had a little bit more pronounced features. We were still able to get about a 72% classification on the validation set, but this is an example of kind of how less diverse data or potentially less refined data captures do have impacts on the model. Still a high-performing model, but there is a noticeable decrease with this data set. This was the final data set, the CNMC data set that was ran against the ViT-CNN hybrid architecture. As you can see, given that it is a binary classification data set, the CNN architecture did struggle a little bit here. We still maintained really strong accuracies, north of 80% during the minimum data sets. The accuracy was almost 90% during training, and we didn't see too much of a dip in validation, but there was some, so that might be indicative of overfitting. Our classification scores are not really comparable to the previous data sets, but they're still showing signs of being a strong classifier, being able to distinguish. Sensitivity is a little bit lower, as it's kind of having a really hard time of saying you are not the target or you are the target. So this data set definitely highlighted one of the limitations of the model.
So here's how the results from all 3 models look all lined up. On Rabin WBC, the ViT-CNN hybrid comes out on top at 98% accuracy and nearly perfect AUROC. But BCCT is right behind it at 95.83%, and it gets there in under 3 minutes of training with no backbone updates. On the leukemia detection task, CNMC ViT-CNN again leads with 89.84% accuracy and 99.84% AUROC, while BCCT and cytodiffusion both land in the mid 70%. The one place cytodiffusion takes the top spot is BCCD with 99.26% accuracy, which makes sense given the dataset has three visually distinct cell types that the SD-VIE encoder separates almost perfectly. The pattern across the board is that all three models work, but the more fine-grained the morphology task, the more the architecture choice matters.
Now let's talk about the lessons that we learned while working on this project. So the first point is like the frozen generative features have a performance ceiling. And then fine tuning the encoder would improve accuracy, but it requires 16 gigabytes of RAM. So as we discussed in the cytodiffusion model, there is a limitation with the frozen generative features, which definitely has a performance ceiling. The second is the class imbalance silently kills metrics. So without weighted loss, model predicts majority class 100% of the time and still hits the accuracy of 68% only. Third point is the merge discipline. So shared modules such as data loader, metrics, they definitely need clear interface contracts because duplicate functions definition silently break at runtime in Python, and we experienced this when we were working on the GitLab together as a team. Talking about the next point, it is about the underestimating the computing requirements. So GPU memory and runtime constraints shaped key design decisions for this project. And the last point is that the white paper sometimes obfuscate key hyperparameters needed for tuning the model to achieve near similar performance metrics.
So to wrap up, we were able to successfully show that across very different architectures, we consistently showed that pre-trained features from natural images transferred to clinical blood cell classification without any domain-specific pre-training. The ViT-CNN hybrid had the strongest overall numbers, with 99.84% AUROC on the leukemia detection task. BCCT matched on standard WBC classification in under 3 minutes of training, which tells us that efficiency and accuracy don't have to trade off. And across all three models, we captured over 91% of true leukemia cases on CNMC. That's a meaningful clinical signal. For future work, the logical next step is patient-level diagnostics. Rather than classifying individual cells, aggregate predictions across a full blood smear to produce something a clinician can act on. And before any real development, we need to validate a larger, multi-site dataset to confirm these results hold across different hospitals and staining protocols. And on behalf of my team, Sean, Darshan, and myself, thank you so much for listening to our presentation.